So yeah, I'm going to talk about a library that I created a few months ago called Caliban. And this library is for creating a GraphQL backend in a functional Scala style. So in this talk, I'm going to first explain why I decided to create such a library. And then I'm going to go through the steps and the design choices that I went through to create the library. And I will finish with a simple example to show you how to use it at the end. Okay, so he already introduced me. If you don't know my name, maybe you have seen my avatar somewhere on Discord or Gitter. So let's start. What is GraphQL? So maybe, how many of you know what is GraphQL already? Okay, so quite a lot. And how many of you have used it at work or in a real-life project? Okay, quite a few. So I'm going to briefly explain what it is so that everybody can follow. So what is GraphQL? It's a query language for APIs created by Facebook, as John said. So it means that when you, just like REST, when you expose a GraphQL API, you can use whatever technology on the server side and the client side. This is only about the way that the client and the server are going to communicate. What is different from REST is that with GraphQL, the server exposes a type schema. The schema is a list of types. They can be enumeration, they can be scalar types, they can be objects. So the schema describes all of the fields that are available, what's the type of every field, and so on. And then the clients can request only the fields that they want. So with a REST API, you can have some endpoint that return a lot of data, like 100 of fields, and maybe the client only needs 3 of them. So you're kind of wasting computing power and bandwidth to send big objects to the client when the client only needs a few of them. An alternative, the client might ask the server to do another endpoint that just returns what they want, but then you get your REST API with many different endpoints for every type of use case the client has. With GraphQL, the server describes everything that they have, and then the client can just pick only what they want. Also, an interesting use case is that if you have a web page, and when you load the web page, you are doing 5, 6 API calls to get the different items, the different data you need to display in the page. So you're losing time, especially the browser limits how many requests you can do at the same time. With GraphQL, you can do a single request and request different fields that are even unrelated. You can get your user data, orders, countries, all at the same time, and just display it. GraphQL supports 3 types of operations: queries, mutations, and subscription. Queries are just for gathering data. Mutation is for when you want to modify or delete something. And subscription is for listening to updates pushed by the server. Typically, queries and mutation are backed by an HTTP API, but doesn't have to be. The spec doesn't say anything, doesn't restrict you on the transport. And typically, subscriptions are backed by WebSockets, but it can be also something else. I'm going to show a quick video demonstrating the experience of writing GraphQL queries on the client side with a tool called GraphQL. So because you have a type schema, it means that the tooling is pretty good because the tools know what the fields are, what fields are available. So the experience is pretty nice for the client developers. All right. So you can see that you have auto-completion because we know what the fields are. If the server has some documentation, you can see some extra detail. If you call a field that doesn't exist, you get the red squiggles, like here. And then the response will match the query format. And you also have rich documentation that comes almost for free. If the server exposes GraphQL, you get that documentation without any effort. All right. So, why creating a GraphQL library in Scala? Because there is already one GraphQL library in Scala, which is called Sangria, and it's a very good library. It was created quite early on after GraphQL was created, and I think it increased, it helped with the adoption of GraphQL. But it has a few drawbacks, especially if you're doing functional programming. The first one is you need to write a lot of boilerplate. If you want to expose a big API and that you have a lot of types, a lot of case classes in your API, you need to provide a schema for every single of your type. So you need to describe every type, give a name, say what the fields are, what the type of the fields are. You need to describe all of that. There are some macros that help you, but you still need to call the macro for every type, and the macros don't support everything. It only supports simple objects and enumeration. It doesn't support still traits extended by case classes, for example. So if you have some of those, which is pretty common when you have ADTs, then you need to specify yourself, describe the schema yourself, and it can be quite cumbersome, and if you have a big API, it's a little bit annoying. Another thing is that it's future-based. So I think there are already a few talks in this conference that say why functional effects are better than features. So I'm not going to explain why. But yeah, it's not so friendly for if you're doing functional programming. There are also a few places you need to throw errors if you want to signify there was an error. So yeah, it's not the most friendly if you're used to the type-safe world of the ZO. Another thing that that I wish were different is that with Sangria, when you define a schema, so for every field you need to describe, you need to give a resolver. A resolver is how do we execute that field? If the client requests a field, how do we find the response for that field? So those are tied together. So if you want to switch, you cannot switch the resolver easily because it's defined with the schema. Okay, so that's it for Sangria. Another thing that motivated me to create Caliban was that I saw a Haskell library called Morpheus that had a very interesting approach to reduce the boilerplate. I'm going to explain it a bit later what it is, but that was quite important for me to see that there was another way to do things. And finally, well, it was pretty fun to start from the spec and to try to build something from the ground. So what were my goals when I created Caliban? I wanted really to minimize the boilerplate so that if you already have a lot of code, it wouldn't take too much effort to create a GraphQL API that just calls that code. I wanted it to be purely functional, so everything had to be strongly typed. I wanted explicit errors. Every type had to be referentially transparent. And I decided to use ZO because it's the most powerful effect type out there. I could have gone the Katz effect way, but Katz effect is kind of the lowest common denominator. So it kind of limits the thing you can do if you're using ZO. And as I'm personally using ZO at work, I wanted the full features, including ZO environment and everything. So I decided to use ZO directly. And also I wanted to separate the schema from the resolver so that it would be easier to switch the resolver for a given schema. So how do we tackle the problem? There are several steps that you need to do when you receive a query, a GraphQL query from the client. First, you need to parse it to see if the query is valid, and you transform it from a string to an ADT. Then you need to validate it. Does the query make sense for your schema? So you need a schema, and you need to validate that every field requested in a query exists in the schema. And there are a lot of other rules that ensure that the query is valid. If the query is valid, then you can execute it, and you get back a result that is returned to the client. Usually in JSON, but it could be something else. So let's start with the parsing. So there is a spec document that is quite easy to read. It's very long, so the first time I read it, I was, okay, it's gonna take me a while, but I think the documentation is very good. There are a lot of examples. Here I put an example of a fragment definition. A fragment is a piece of query that you can reuse in multiple places, so you don't need to repeat all the fields. You can put them in a fragment and reuse the fragment. So you can see the kind of the way the spec defines how types are. So for example, a fragment spread is 3 dots followed by a fragment name and optionally a list of directives. And you can see a fragment name is a name but not the word on. And somewhere else there is the definition of what is a name and so on. So a lot of types. And to implement it, to implement the parsing, I decided to use a library called FastParse. It was mentioned yesterday in one of the talks. Library from Lee Ahoui. Why did I choose to use that? Because as its name indicates, it is fast to execute, and also fast to develop with. The documentation is fantastic. There are so many examples that I didn't even need to ask any question on Gitter or anything, because everything was there. So that was pretty straightforward. Here there is an example of how do you work with FastParse. So for example, a name can be any character that are underscore, A to Z, lowercase or uppercase, followed by any character between underscore, 0 to 9, A to Z, repeated any number of times. That's how you define the name, and then you can reuse that name for bigger type, like a fragment name, for example, is any name that is not expressed with filter, the word on. So the code looks actually very similar to the spec, which is pretty good because you don't need to juggle when you go from one to the other. So the parsing is simply done with FastParse. Now let's talk about the schema. So what was this idea from Morpheus that I really liked? So most GraphQL libraries, not just in Scala but in every language, force the user, the library user, to define manually what are the types and the fields and the type of the fields and so on manually. What Morpheus did is that they didn't have such thing. They just used basic types, well, in Haskell in their case, to describe their schema, and then derive the GraphQL schema from the basic types. Let's look at an example. All right. So there are too many cats, so I decided to. So let's start with a very, very simple API that returns a random pug with a picture, for example. That's the reason I use Instagram, basically. So on the top you can see in the GraphQL format how does a query look like. So it has a field called pug that returns a type, an object of type pug. The exclamation mark means that it's non-null, so you will always have a response. Without the exclamation mark, it means that it's optional. It might return null in GraphQL. So this is actually very, very similar to a simple Scala case class called queries that has a field named pug that returns a pug. So why don't we use that case class to represent that schema? Let's take a more complex example. So here we have the type pug that has a name, a list of nicknames, and a picture URL. That is really similar to a case class that has the same type. I used a list for the nicknames, and I use an option for the picture URL because you can see there is not the exclamation mark. So it means it can be null. So in Scala we just use option to express it. GraphQL also supports enumerations. As you can see, the color enumeration. So we can express it with a simple Scala SIL trait extended by case objects. But now what if we want arguments So instead of just getting a random pug, we pass a name, and then we get a result. So how do we express that using basic Scala classes? Well, we make our field a function from a pug name to an option of pug. So why did I use a pug name case class, by the way, and not directly a function from string to option of pug? That's because we need a way to name the argument. You can see on the top that there is the argument is called name. So if I was using a string, there would be no name. So I have to use an intermediate case class just to name the argument. So here we are returning an option. What if we want to return an effect? Because maybe we need to get the data from a database. Well, the GraphQL type would be exactly the same, except that your case class can return a function to a task or an IO or a ZO or whatever. So if we define our schema using case classes like that, how do we define the resolver? Well, the resolver is simply a value of the type of the case class that you just created. So the resolver is actually a record of function that explains how to gather every of the fields. So really no magic here. I haven't introduced a single new type yet. So now, let's say we use those case classes to define our schema. How do we get from the case class to a GraphQL type, and how do we resolve it? So for that, Caliban uses a type class that's named schema. So it's schema of R and T. The R here is the same R as in ZO, so it means that you might need an environment of type R to run, to resolve the queries of the schema. And the T is the type, the data type that you want to create a schema for. So to create a schema, we just need to implement two methods. The first one is toType, it means toGraphQL type. So how do you go from that Scala type T to a GraphQL type? Underscore type, that's the GraphQL type name. I called it underscore because that's the way GraphQL calls it. So I just try to match exactly their names. There is a isInput parameter. That's because in GraphQL, the same object, if it's an input or an output, is a different type. So it's not the same type if it's given as an input or written as an output. So that's why we need to know, to create a GraphQL type, we need to know if it's input or output. And then we need to implement a resolve function where given a t value returns a step. So what's a step? A step is a description of a computation, a bit like ZO is a description of an effect, that tells us how to gather that field. So what can be a step? A step can be a pure value, so that's very simple. Like for a schema of string, well, the value is just a string. There is nothing else to do. It can be a list of steps, so we need to run multiple steps. It can be an object. So an object is similar to a list, except each step has a name. And in a list, it will be always a list of the same type, but an object can have multiple types. A step can be an effect, so it will be basically a wrapper around the ZO effect. And a step can be a stream. It will be a wrapper around the ZO stream. So that way you can express a lot of different possible computations. Let's see an example of schema for string. So for how to implement the toType, we just return a GraphQL type object with a kind. The kind here is scalar. The kind could be also object, list. There are various kinds. And a name. So the name here is just string. And the result function is just a pure step. We have a string, we just return it. There is nothing to run. There is no effect here to run. So Caliban provides schemas for all the basic Scala types, list, option, int, string, and so on. But then, how about if you want to expose an API, you're not using only Scala basic types, you're also using your own types, your own case classes, your own seal trait. So do you have to write a schema like that for every single of your types? No. How do you do that? Anybody has an idea? Better. Magnolia. So yeah. I'm using a library created by John Pretty called Magnolia. And what Magnolia allows you to do is to automatically create at compile time instances of a type class for any case class and filtrate. There's only one precondition, is that you need an instance of any type used inside the case class. So if your case class uses an int and a string, you need an instance for int and for string. And if you have them, then you can create an instance for your case class. So Magnolia is really nice because it's very easy to use. I could have written my own macro, but then I would have had to learn how to write macros. But with Magnolia, you don't actually need that. Another thing that's really good is that it doesn't bloat your compile time. It keeps your compile time pretty low. I quite appreciate that. The documentation is really good. There are a lot of examples also in the GitHub repository. There's just one thing that's not perfect yet for me. That is that if you have very complex nested case classes and you're missing an instance for a type deeply nested, the error message sometimes are not the most friendly. But it's getting better. The latest release of Magnolia 1 or 2 weeks ago actually improves the situation. So hopefully it will become perfect. So how does it work? Very briefly, it exposes, you have two methods that you need to implement. Basically, it gives you a case class object that contains the name of your case class, the name of the fields of your case class, the type of the fields, and from that metadata information about your case class, you can create, in our case, a schema, a GraphQL schema based on all this metadata information. And the dispatch method is the same thing for a filtrate. So you don't actually need to know about it if you just use the library, but that's how the library works to create schema for all your case classes. So now we have a schema. We need to validate it. How to do that? Well, we have to go back to the spec and read it, and read all the rules and implement them. This is not the most fun part of the implementation of the library, especially because GraphQL was initially developed in JavaScript. The first implementation was in JavaScript. All the little algorithms in the spec are using mutable variables and null, and you cannot easily transpose it to Scala, so you have to change it a little bit. It's a bit boring. Now the execution, that's more interesting. So you have your query that's properly parsed and you want to run it. How do you do that? All right, so we have our schema, so we know what types and fields we have, and we have a resolver that tells us what function to execute for every single field. From that, we create what I call an execution plan, which is a tree of steps. So it's a big tree, and at the root we have a bunch of fields, and then for each field we have other steps and so on. So we have this large tree that we build at the beginning. Then when we get a query, we only want some fields. So the first step is to take that big tree and cut all the branches that we don't care about and build a smaller tree with only the fields that the client wanted. Then we have another reduce operation, which is that we try to make the tree even simpler, because sometimes a tree could have an object step, and then every leaf is a pure value. We can transform this whole object into a pure value. So we try to reduce the tree so that we mostly have pure values and effects. And the effects, we can't reduce them because we need to run them in order to know what's the next step. So we reduce that tree, and then we run the effect. If we run the effect in a naive way, we just fold the tree from the top, and then when we run into an effect, we run it, and then we continue, we find another effect, we run it. That works, but it's not the most efficient. And you quickly run into a common problem, which is this problem. Let's imagine you have a query and you request a list of orders. And then in the back end, you call the database to get the orders. And then for each order, you have a customer ID, where you need to return the customer names. And you need to do another DB query to get the customer name from the ID. If you do it in a naive way, you're going to end up doing one query to get the orders, and then n queries to get the name for each ID. The more nesting you have, the more this problem can become important, because it grows exponentially. So it doesn't work so well if you just have the naive approach. I illustrated here with a simple zero example. It's the same thing. You have a list of, you have a function that returns a list of user IDs, and then for each user ID you call getUserName. So you're going to end up doing 1 plus n queries to the database. So how did we solve that in Caliban? Let me introduce you a new Z data type, ZQuery. How many hours since the last Z data type? So ZQuery is very, very similar to Zio. You can see I basically just replaced Zio by ZQuery, and the code is same. But the way it will work is quite different. The for each part here, when you run the ZQuery effect, it will look at your tree and try to find every effect that it can run without being blocked, and then gather them, run them in parallel, and then do another pass. Once we have the result of those effects, try to gather all the next effects that don't depend on each other, run them, and so on. So it parallelizes queries as much as it can. If you have the same input, it can cache queries. So let's say in our previous example, we had several orders from the same customer. The ZQuery would gather the customer name once and will not do it multiple times. And then, what did I do? All right. Not sure what happened. All right. Okay. So, oops, spoiler. Yeah, the last thing I wanted to say is that if you provide a batching function that takes, for example, a list of IDs and that can return a list of names, ZQuery will use that batching function instead of requesting items one by one. It's optional. It cannot guess how to batch elements. It only works if you give a batching function. So yeah, ZQuery was implemented by Adam Fraser. He's really everywhere. I'm very thankful for this contribution. It's based on a paper on the Haskell library in Haskell. It's also done by Facebook. If you're interested, I recommend reading this paper. It's pretty easy to read. And it's actually not specific to GraphQL. It could be used in many other situations. So we intend to extract it into its own library at some point in the future, so that you will be able to use it in any context. All right. Just a word on introspection. So introspection is the process that allows the tool that I showed at the beginning to know all the types that are available on the server, and so that it can show this nice documentation and have the autocomplete and so on. So the introspection is just like a regular GraphQL field that you can gather. You can ask a list of types and so on. So I just used the same thing that I showed before. I created this case class introspection with those field names. So here again, the underscore are because that's the way GraphQL wants the fields to be named. And that returns your schema. So I just used the library itself to implement the introspection. That was actually a good way to test the library, because the introspection query is really, really long and complex because it's asking everything. So it was a good way to see that it actually works. So now let's see a simple usage of the library. So what you need to do to implement GraphQL API from your existing code. So first you need to define your queries, mutation, and subscription. So you just need to create some root case classes with a field per each operation that you want. Then if you use any type that is not a case class, not a sealed trait, and not one of the basic Scala types, you need to provide a schema for it, because otherwise you won't know how to handle that type. I will show an example just after. You need to provide a resolver, so a value for the case class that you created, and that's it. So let's see it in action. So again, I have those case classes that are similar to the previous examples. It will generate the GraphQL schema that you see in the bottom. One difference with the previous example is that I used non-empty string instead of just a string. So here, it's a non-empty string class from the refine library. So Caliban and Magnolia will not know how to handle this field. So I could have written the schema myself, but you can also reuse existing schema if your type is similar to an existing type. You just need to provide a function from your type to the other type that you want to reuse. So here I just reused the string schema, and I use contramap and gave a function from a non-empty string to a string, so dot value, and that's enough to say how to handle non-empty strings. So if you're lucky, your type is similar to an existing one, and you can do this very easily. But you can also completely have your custom schema definition if you want to. We provide a resolver, so let's say we have some existing API, get bugs. We just create a val queries of that type that calls those functions. And then we create a root resolver. That's the, I think that's the first Caliban type that you actually need to deal with. That takes three parameters, queries object, a mutation object, and a subscription object. You don't have to provide all three of them, only the queries are mandatory in GraphQL. So if you don't use mutation and subscription, they will just default to unit. So you have this val resolver, and then you call the GraphQL function that returns an interpreter. And the interpreter can be used to run queries. So in the little example here, we have a string query, and we pass it to the execute method of the interpreter, and we get back a result that we can display, and it's going to show the JSON structure of the result. In practice, you will often not need to call execute yourself, because you will probably use an HTTP backend. So Caliban comes with an HTTP4S module. So you just need to pass your interpreter object that you created before, and it gives you an HTTP4S route that you can serve on any port or server that you want. So it's really a matter of 3 lines to get it running. There is also a make WebSocket service function if you want to get an HTTP route for WebSockets, which is useful if you use subscriptions. One takeaway from building this library is that if you pick a few amount of dependencies and you pick them well, modern dependencies, you can get some benefits for free. So I discovered that I could support Scala.js without any effort because FastParse, Magnolia, and Zio support Scala.js, which is pretty cool because it can be useful to share types from the client and the server if you use Scala.js. What if you really like cats? Then there is also a Caliban cats module, and you can use variants of the execute function using F instead of Zio directly. And there is also a version of this to get an HTTP route of F instead of an HTTP route of Zio. So it means that you can use that with Catsio or Monix if you want to. Last word on performance. So the performance might not be so important because at the end, if your API, if whatever you do, your effects are slow or are doing some computation or I/O, the performance of Caliban itself will be almost nothing. But it's quite important to keep the overhead as minimal as possible. So Caliban is really fast. I'm not going to tell you how much faster it is, but you can check the benchmark module on GitHub to see it for yourself. So I have some plans for the next releases of Caliban. I'd like to, well, it's almost done, not merged yet, but almost finished. I'm adding a query analysis module so that you could analyze a query before the execution and potentially reject it. Like, for example, if the query is too complex, or if maybe if you get attacked and someone sends you a crazily deeply nested query to try to make your server crash, you can block it right away. A common use case also is to calculate the cost of a query. The GitHub API has that. For every query, it calculates a cost and it returns the cost in the response. So that's possible. That would be possible with the query analysis feature. Right now, there is also you can add some middleware around each query execution. So you can, for example, add a timeout on every query or add a log somewhere for every query. So that is already there. I would like to add it at the field level. So some people might want to do something on every field, like measure how long it takes to query each field and maybe store the metrics somewhere. So that's something I will work on. There is someone working on code generation. During the whole talk, I was focusing on existing Scala code and exposing a GraphQL API from it. But if you go the other way around and you have a GraphQL schema in the GraphQL language and you start making an API, the code generation would create all the base classes from the GraphQL types. So that, I think that could be pretty nice to bootstrap your Scala project. I would like to have other HTTP adapters. There is someone who did the REST part of HTTP, but if you want to contribute, there is also still the WebSocket part to do, and maybe other HTTP frameworks. That would be nice, so that it's really, as for HTTP4S, a single line and you can get started. And I'm starting to think about why not extending Caliban and also offer client support. So I didn't start yet, but that's something that I'm thinking about. All right, so you can find more information on the website. I tried to spend some effort making the documentation nice. You can find me and others on the Caliban channel, on the Zio Discord. You can find me on Twitter. So I encourage you to try it if you're interested and give me feedback. It's a pretty new library, so I'm very motivated to make it the best as possible. Thank you for listening.